Hello, this is the submission of the assessment modeling a robotic manipulator, and my name is Matheus Abreu. So the task for this assessment is to design a manipulator that can pick a festo puck from the floor and place it on shelves that are placed in these locations here: 200 millimeters, 400 millimeters, 600 millimeters. Um, and the manipulator is on top of a turtle bot, but you do not need to design the turtle bot. And also you do not need to design the shelves. You need to select the Dennevit-Hartenberg parameters of the robot. And these kinematic parameters will describe the robot. So how I started with forward kinematics. So I'll show this VI first. If I run this, you can see that all my joint positions are an angle of 0. And then I use this VI to get my Dennevit-Hartenberg parameters and to find the best starting position for the robot. And this is useful because this initial position can then go into the start of the inverse kinematics. Can be used as the initial position for the inverse kinematics VI. So with this, I can show that this VI works. I can move it around. So I move the first joint, but we don't want to do that because that moves into the y-axis. So if we want to move this joint, for example, up, we got here, then back to 0. I started with this joint negative because we are these manipulators on top of the turtle bot. So it doesn't matter if the arm is going downwards like this. And yes, I use this VI to tune and find the best starting position. Okay, so let me stop this one. The next VI that I created was this inverse kinematics one that was used to send different locations to the robot with inverse kinematics. So with the end, so the end effector could be at certain positions. If I click play, you can see now is at this strange position because it's 0, 0, and 0. But if I set it to position 0, it's picking the festo puck from the floor, and then position 1 is placing at the first shelf, position 2 is placing at the second shelf, and position 3 is placing at the third shelf. So, and you can see we have the strings here saying what it's doing. And the idea of this was to find the best positions and then create a trajectory out of these positions that were found. So this is a simple VI. Here's the block diagram. So I have this. So I have it as the start. I have it the starting position set to this, which I determined using the forward kinematics VI, and then my DH parameters, which I'll talk more in depth in the next VI. And then I can, so with the manual control, I can set X, Y, and Z, and this will be fed into the inverse kinematics block, which does all the calculations for us, and then updates the plot and shows the picture, right? And I have this K structure here. I have position 0, which is X is at 0.5, and then X is at 0.7 at position 3, which means that I assume that the shelf was 200 millimeters in front of where the puck was on the floor. Then position 3 is at 0.6, so 600 millimeters, so it's the last shelf. Position 1 is the first shelf at 0.7 as well. X and Y stays the same because we don't need to move in the Y direction. And position 2 is the second shelf at 400 millimeters. Okay, so the last and final VI. So we don't need to save this. So this VI will is the final VI. And if we put some speed here, we can see that we already have our manipulator at the starting position. So, okay, let me show what it does first. So if I started, so this slider here is the intermediate points, and the more intermediate points that I have, the slower it gets. So I can show first the manual jogging, and this I'm just increasing the X. I can do it a little bit faster, increasing the X, decreasing the X, and increasing the Z a little bit faster, increasing the Z, decreasing the Z. And I'll set it to a little bit slower and start the automatic path. As you can see, it is picking from the floor and placing on the shelves. You can slow it down a little bit more. So it's always picking from the floor at position Z equals 0 and X equals 0.5. And then it's placing on the shelves at X equals 0.7 and Z 0.2 for the first shelf, 0.4 for the second shelf, 0.6 for the third shelf. And it just keeps looping, and the arm keeps performing the task. So I'll stop the VI and pull up the block diagram. Okay, so these are my DH parameters. I have the first link length as 0.01 because it's not really relevant to the task. So, and at 90 degrees, because we don't need the rotation. That's why it's so small, because we don't need this rotation in the y-axis. So this is the only joint that's at 90 degrees, 1.57 radians. Then all the subsequent joints, they are at 0 degrees and radians. And you can see here that the length is 0.4, 0.3, 0.3, 0.1. So the total length of the robot is 1.11. And this means that we can extend totally horizontally 1.11 meters and totally vertically 1.11 meters as well. Then this is the initial position, same as the previous one. And this is how so here I'm getting the current angles from the shift register. The shift register keeps updating every time the loop is run. Then I am converting this and getting the current X, Y, and Z positions, feeding this to this case structure. And the case structure is determined by the switch here, which is either automatic or manual. And here I'm doing the manual, the manual. So I can either go up on the X, go down on the X, go up on the Z, go down on the Z, and then I display my values. And this was done to adjust and find the best positions to pick and place the pucks. And then here is the automatic path. And this X, Y, and Z values are then fed into this transform. So it creates a transform, then feeds into this array builder. So I have an array here. Then the array is fed into the path planning. And I also use forward kinematics to get the transforms of current joint angles. Then I feed this in. And here I'm limiting rotation, which is this last three values here, which is set to 0. Then X, Y, and Z translation is allowed. And then I update the plot and display the picture. And I have the shift registers here, which do the same thing, update every time the loop is run. And yes, this is my project. Hope you enjoyed it. And thank you very much.